When you look at an offshore wind farm, the most obvious threat to the equipment seems to be the ocean itself. But the forces that actually destroy these multi-million-dollar installations usually aren't weather-related at all. There is a violent, invisible storm happening entirely inside the grid. To find the source of that turbulence, you have to follow the power down beneath the ocean waves, into the massive network of submarine cables connecting the turbines to the shore. Comparing a submarine cable to an overhead line, the submarine cable is wrapped in tight insulation and surrounded by conductive seawater, acting like a giant capacitor. Stretching for miles, it stores and holds a massive reservoir of energy as electric fields. Sitting in a steady state, that stored energy is completely harmless. The problems only start when an operator flips a switch to open or close a circuit. The infrastructure we need to bring offshore wind to land creates a tightly coiled spring of electrical tension, just waiting for a trigger. That trigger is usually pulled inside the offshore substation, which acts as the mechanical control point for the entire grid. To route power or clear faults, operators use a device called a vacuum circuit breaker. The breaker operates by physically pulling two metallic contacts apart inside a pure vacuum, instantly interrupting the flow of electrical current. This graph tracks a split-second race. The rising wave is grid voltage, trying to jump the gap. The straight line is the vacuum's growing insulating strength. In capacitive networks, voltage repeatedly wins. It punches through the vacuum, causing rapid-fire arcs called pre-strikes. Each of those microscopic arcs launches an incredibly steep, violent voltage spike down the submarine cables, where it reflects and amplifies against the ends of the line. A routine switching operation, meant to protect the grid, unknowingly unleashes a barrage of high-frequency shockwaves directly into the isolated network. Those high-frequency shockwaves travel along the cable until they slam into the wind farm's step-up transformer. Normally, a transformer is guarded against outside threats. Standard external insulation easily repels traditional dangers, like a lightning strike on an overhead line. This visualization shows the mechanism of destruction: internal resonance. The incoming switching shockwave overlaps exactly with the natural vibrating frequency of the transformer's copper windings. Because these frequencies sync up, voltage amplifies locally, multiplying its power far beyond what internal materials can handle. The trapped voltage builds until it violently flashes over, arcing directly between the winding discs and bypassing all the standard insulation. The high-frequency transient doesn't break the door down from the outside. It acts like a targeted acoustic weapon, shattering the transformer from the inside out. When transformers are under threat, grid operators rely on an ultimate shield to protect the equipment: the metal oxide surge arrestor. Under normal conditions, an arrestor works by briefly clamping down on fast, microsecond-long voltage spikes, safely bleeding the excess energy into the ground. But the exact same cable switching events that cause high-frequency shockwaves also give birth to a secondary threat: temporary overvoltages, or TOVs. This timeline illustrates the difference. A standard transient is a sharp microsecond spike, while a temporary overvoltage is a rolling harmonic resonance sustaining for seconds. This prolonged overvoltage triggers thermal runaway. The arrestor's physical blocks continuously absorb heat, pushing past their maximum thermal stability limit. Engineers call this physical outcome the crispy factor. The arrestor loses its ability to block current, cooking itself until the ceramic core cracks and shatters. The very devices installed to protect the grid are roasted alive by the grid's own physical properties. We are currently in a massive global push to deploy offshore renewable energy arrays, connecting thousands of turbines across vast stretches of ocean. By adding hundreds of miles of highly capacitive submarine cables to traditional grid components, we are inadvertently creating an entirely new, highly volatile electrical environment. To survive this invisible electrical storm, engineers have to completely rethink grid architecture, breaker technology, and insulation coordination from the ground up.